Now, about simulation of real-world incidents. So previously, I've shown how we chose which scenarios to take forward into the simulation, and this is now about how we actually implement those in the simulation. We start with a model. We need to have a digital representation of the real world, and that starts with a LiDAR scan. As shown in the picture, you can see a point cloud of a part of the SMLL route in Woolwich. In fact, you can see our new SML office in the corner there. This was built originally as part of a previous project called BIMCAV, where we looked at the benefits of building information modeling to help support the adoption of connected and autonomous vehicle technologies. Now, as we started building SMNL, we continued to invest more on this model, and we basically ended up having a digital twin of all the SMLL routes, which are over 24 kilometers. Now, this model, as I said, was this point cloud was then used to build the BIM model, as can be seen from this picture. And for some of the areas, we actually enhanced this model even further, and we applied, we have some of the textures applied for a smaller area, and we have that version for some of the routes as well. So we start with the digital twin model, but the model itself is not enough for the simulation to run. We chose Carla open source simulation platform. It's a widely used simulation platform used for autonomous vehicle, automated vehicle research. So we chose to use that one for this specific project. And what we had to do is we needed to supplement the model with some additional data. We basically matched and created an OpenDrive file, which is a common format used between different types of simulators to define the geometry of a road. And here you can see a visualization of the matching OpenDrive file for this loop that we brought into Carla. And when we have these two elements, we are then ready to start simulating. We also had to add extra traffic rules. For example, here you can see we have some traffic calming measures in Royal Arsenal area, which we brought in there by introducing the necessary giveaway values and some of the junction models. So at this stage, the vehicles are following a simple line following algorithm, but they can react to objects on their path. They can give way to each other, and they can obey things like the junction priority and all that. So this is very good for the other vehicles in our simulation to behave in a sort of realistic manner. But what we are really interested is in the ego vehicle, the vehicle that we're testing. And this is where we tapped into the Ross bridge and the Autoware bridge, and here you're seeing actually a visualization of the information, the sensor data coming out of Carla live and fed into RViz. On the right side you're seeing the LiDAR data, and on top you can also see other data such as the distance to the nearest surface applied on it running live, and you can see the vehicle have basic functionality such as giving way to oncoming vehicles and all that. This helps us basically creating the necessary nodes to connect different automated driving algorithms into our simulation. So at this point we had the necessary environment. Other actors can behave in a certain way to have simulations run by themselves. But what we really wanted to do was to bring these scenarios we talked about, and that's where the scenario runner comes in, which is a Python code. It's a Python interface through which we are basically bringing the scenarios from RAIDs into the simulation, and this code includes things such as the position of different actors on the scene, where the ego vehicle was, where the pedestrian was in different time frames, and it can control and recreate the incident as it was, as we have the data for. But obviously what we are really interested in is not just recreating the incident as it is. We want to replace the vehicle in this incident with our ego vehicle, and then we want everything apart from the ego vehicle to be the same as the incident, so we can see how the ego vehicle reacts to the same scenario, if it can behave better than the human driver did in that specific case. But we're not only stuck with this, and what we've done is, obviously the race case is the starting point. What we've done is we parameterize each of these incidents, and we have run many different iterations of the scenario by controlling different parameters such as the speed of the pedestrian jumping, the time of the day, the weather conditions, the light conditions, the position of the bus. And these were all done automated. This process was completely automated through the scenario runner code. And in the end, for the specific proof of concept, I think we did around 1006 iterations of this specific case. And then we ended up with lots and lots of results coming from each of these scenarios. So to wrap it up, we started with the selected scenarios with the scenario description language. We put these scenarios into our digital twin. For example, we had the geometry and the matching OpenDrive for the simulation environment. And then the simulation was run on this environment, but all the vectors and other elements, environmental elements such as time and weather, were all controlled by the Python client, the scenario runner. And then into the simulation taps in the AV model. Basically, the sensor output is taken out from the simulation through the ROS bridge and then fed into the model, and then driving input is provided back into the simulation, which then provides results for us to assess.